Hey everybody, and welcome to another episode of Space Science with Python. Last time in our Cassini CDA project, we were considering previous calibration functions to compute the velocity of impacting dust particles that were flying into our cosmic dust analyzer instrument. And the functions are already were already being used in different scientific publications and so on. And they are also high polynomial fits of the calibration data I showed you last time and also in the video before. And today we are trying, or we will start working on a machine learning based approach where we will use a small, quite shallow deep learning network to get some kind of fit on our calibration data. So the goal today is not really to have the most fanciest solution, it's more like a starting point. And also I would like to show you the pitfalls and also what we will do in the next tutorials to improve also our results. So today's session is divided into some parts like data preparation again, also data pre-processing, creating the machine learning model, and also showing the resulting solution space. And I would suggest, instead of talking too much, let's dive directly into the code. Okay, everybody, so we have here our third script, the machine learning calibration IPYNB, so Jupyter Lab notebook. And you see here, again, we have our different sections, so in total 5. So also the video on the bottom, the player has also the corresponding sections that correspond to these subtitles. And this is the one thing. And the other thing is also that this script is also available on GitHub for free. So the link to the script and also my entire repository is in the description. So feel free to open the notebook and open GitHub and download the repository, or also write issues if you find any bugs or what's or not. So first of all, I would suggest we start the read in the data. This is basically the same thing as we did it the last time. We will exclusively focus on the IAD, on the larger target data. So you see here we are also considering only amplitudes, QI amplitudes that are larger than 0 femtocoulomb, and also rise time that is larger than 0. So our data frame consists in total of 1,600 rows and 12 corresponding columns, but today we will only focus on the QI channel. So the PSU velocity, the QI charge, and the QI rise time are the values we are looking for today. Now, I would also suggest that we plot now the rise time versus the amplitude more the PSU velocity with respect to the rise time and the amplitude, that way. And why are we doing this? Well, maybe we see another shape in 3D where we can maybe create a more sophisticated calibration function that is differentiates between more, or considers more input parameters or features. So this is what we do now in this section, and I would like to do it also a little bit interactively. And for this we have to install a Python library. I also already installed it, the IPYMLP. This will allow us to do some interactions with matplotlib in 3D, but be aware that, well, this is not very powerful. Though there are other tools that can be implemented into Jupyter Lab, and we will do this also next time. But today, let's stick with matplotlib and do this. I won't execute it here now because I already installed it. But but I need the widget, of course, for matplotlib. So let's execute it anyway. The requirements are already fulfilled because I already prepared everything beforehand, and now we can execute our script here that creates a scatter plot in this 3D projection, as you see here in this line. So we are simply considering QI rise time, charge, and the PSU velocity, but the charge is considered in a logarithmic scale. So here in this upper part, you can also change it to maybe the QC or QT channel or so, just to get an idea how the distribution looks like. Now the scatter plot is also color it a little bit. So we color our scatter plot also scaled by the velocities. So higher velocities have a different color than slower velocities, and we use the NiPi spectral CMap, which I like. Do some titles and labels, some formatting. We add the color bar, of course, and then we can execute the code to have this 3D and 3D plot. And you get already a good impression without rotating anything. You see here the rise time in microseconds from around 0 to 80, and the QI charge in log femtocoulomb, which is between here 0 and 3.0, and the velocity ranging from 0 to around, I would say, 60 or 50 kilometers per second. You see, as also shown in the last video, the shorter rise times correspond to higher velocities. And this was what we have seen here. So we saw only, let's say, a projection on it without considering the charge of the particle or the amplitude. And now if we consider the amplitude, we see that smaller amplitudes correspond also for smaller rise times to slower velocities. And we can emphasize this a little bit by rotating it now. So no, this is not a low FPS video or something. It is really that slow in Matplotlib. But I think you get the gist if I rotate it a little bit. And of course you see also some gaps and so on. So we have to be really careful how to model this with a machine learning algorithm. And yeah, you see it's not that fast, but you get an idea. And next time we will use other libraries to interact with these things. Yeah, and maybe I will also create some kind of 3D, or some kind of GIF that I could then upload, for example, on Twitter or Mastodon for better visualization. The next step is our data preparation. Now we would like to make a machine learning algorithm to really create some kind of regression plane that describes the data, right? And for this, we need to do some data processing. First of all, I would consider to add a new column with the log 10 amplitudes. So we do it here. Then we are only filtering out the rise time, the log 10 amplitudes, and also the velocities. Then we shuffle it a little bit here because we do not know if the order of the data frame is somehow already biased. And then we use scikit-learn model selection train test split function to create a training set and a test set, as well as the corresponding not labels, but in this case the corresponding velocities. So we do a test size of around 20%, so 0.2, and this is what we do here in cell number 9. Now we have to also reshape a little bit the data, because Keras expects a certain format where we don't have simply the 1300 data points in an array, but each entry is each needs to be considered as an own dimension. So we have to reshape it here to 1003,1. Anyway, we are doing now also a standard scaling. So the standard scaling means that we are subtracting the mean of the data and then dividing by the standard deviation. Also, this kind of scaling is something we will consider next time, whether it makes sense or not, right? Or whether we can use also other scalars. And we do this for the for the training as well as for the test data. And we also do it for the corresponding velocity. So we create only one scalar that is transfitted on the training data, and the test data is only being transformed based on the scalar. So this is what we do here in cell number 11. And then at the end of the day, we can verify that we have a mean and a standard deviation of 0 and 1 respectively. But yeah, okay, 0, almost 0, but a very, very small number. We can start now doing our machine learning stuff. And I would suggest let's work a little bit with Keras, so the TensorFlow high-level API. And we create a very small and simple neural network just for testing purposes, and then it's an introduction into this regression tutorial. So our input is here defined as keras.input. Our shape is 2, the rise time and the log 10 amplitude, but of course it's the scaled one. Let's add maybe also 2 layers with only 64 and respectively 32 units, and also with a ReLU activation. And then as an output, we just have a dense layer again with only 1 unit. And the 1 unit is the PSU velocity. So I just gave it here also a small name. We use then the Keras model API. There's also the sequential and also other APIs, but I like the model one because, well, of course you can do it here also with the sequential because we have input, 2 dense layers and output. But the model API is something that is more flexible, and this is also something we will use later. And yeah, I mostly use only the model API, so it's quite convenient. Now we can also compile it. As a loss, we choose the mean squared error, so the MSE. Again, we can also choose another one, and I will talk about it next time. And as metrics that we would like to record, we choose the root mean square error and the mean absolute error. So these are also the 2 metrics we considered last time for our other calibration functions. Now we do the fitting, with the scaled training data and also the Y, the velocity values, and then some epochs. We do not have a callback or something or interrupt the training for the best loss or something. No, we simply run through 100 epochs and check the corresponding results. And we have a validation split of 25%. And this 25% corresponds to the training data that is already 80% of the entire data. So that at the end of the day, we have 60% training, 20% validation, and 20% for the training. With verbose equals 0, we will not get any output of the training process, so it will be quite silent because afterwards we would like to simply plot the loss function of the fit, so the loss and also the validation loss. So let's wait for a few seconds. This takes like, I don't know, 10-15 seconds maximum. So there's no need of using not TensorFlow, but there's no need of using Google Colab or so. And here you see the result now. So we have here the loss and the validation loss. Validation loss is also lower than the loss function. We'll talk about it also next time. And you see at some point we reach a plateau, so there is no improvement at all. But again, today is just the introduction. Let's have also maybe a quick look at the model itself. So we have around 2,300 trainable parameters, and then we can also evaluate it. And evaluate means that we take the test data and it is evaluated based on the loss, but also on the metrics we provided. And you see here the root mean square error and the mean absolute error provided here. And these are the values. So here's the RMSE and here's the MAE, but they are scaled. So let's rescale them maybe. So we store the RMSE scaled and also the absolute error scaled, and use the Y scalar with the inverse transform function to then really get the values in our actual physical space, so kilometers per second. So let's execute it here, and we see that the values are really bad, like 14 and respectively 13. If you recall the prior calibration functions, they were like around 8 or 5 or something. So it's not the better solution. Maybe also not comparable because it's 2D, but there's, I think, room for improvement. There is one advantage now that we did it in 2D, or let's say in 3D. We can now also plot the solution space in 3D, and this is pretty amazing. So what are we going to do now is we define a certain range, I would say between 1 microseconds and 0.5 log 10 amplitude, and 60 microseconds and 2.5. So this is like the minimum rise time, maximum rise time, the minimum log 10 amplitude and the maximum log 10 amplitude. We transform it. We create then 2 arrays. These arrays range from the minimum to the maximum value in 100 steps. And then we apply a mesh grid so that we get a matrix basically that we can then feed in our neural network to get the corresponding velocity results. And what we do now here in cell number 18, a little bit of magic, but you can maybe do some prints and see what really happening step by step, or some variable explorer. We are iterating now through the scaled mesh grid, let's say, and what we do is we we first of all do the inverse transform, so also in a format that we can later create a surf plot, and the scaled values are put also into the model. With model predict, we get an array of results, so the corresponding velocities. The velocities are scaled though, so we have to put the results into our y-scaler and do an inverse transform and also shape it in a format that we can plot it in a second. So if this looks a little bit magic, just plot this a little bit, you will see that the shape we have to enforce some kind of shape that is required for matplotlib to understand the data. And now the last plot here is almost a copy of what you have already seen, but there is one small add-on, this plot surface command, where we now plot the solution space of our neural network that is then showing how the regression plane looks like. So let's execute it, and we get here now the corresponding result. So this is now the plane that is drawn on our data. And I would say for a very first approach, it looks quite okay. Do we have even negative values? I hope not, because it wouldn't make any sense. You see, it's quite difficult to really go through it. It's really, really bad. And you see there's also some deviations where we could conduct some improvements with our model. So also here we have only a few data points. I don't know how the model reacts to that. So this is something that needs improvement, but it gives you a first impression what with a small script that you can write maybe within an hour, or with ChatGPT maybe within a few minutes, to get some kind of script that helps you creating your own regression functions for your instruments in the laboratory, in your industry product, or anything else. So this is just 2 dimensions. We will also increase the dimensionality later, but I think this is a very nice visualization to support, to help one to understand how the solution space of a neural network looks like, because mostly it is like a black box, and this gives it, yeah, some kind of a shape or a face, so to speak. This was now the small introduction into the machine learning calibration function, and you've seen that we had some overfitting. Our mean absolute error was not that good, and the prior calibration functions are way better, although we did it in 2D. And you've also seen that some data points are quite underrepresented, but also very important, especially the ones with high velocities. And if you consider doing the training, validation, testing split, well, you can imagine that a lot of data points are being lost in this process, where the machine learning algorithm doesn't see the data for the training process. Now, additionally, there are also a little bit where we just didn't try any hyperparameter tuning or something like that, or regularization. We also didn't consider any other loss functions. Maybe there are other loss functions that are more powerful. So I would suggest that next time we are diving a little bit into this. So how does regression with deep learning work, and trying to improve our algorithm a little bit. So today is now, let's say we set the foundation, yeah, and next time we will try to improve everything to build a proper house on the foundation. And until then, you can download the script, and you can play around with the architecture, you can play around with the loss functions already and see how things change, or maybe apply this to your own needs and your own calibration work if you are maybe working in an industry or in a university, academia, or what's or not. So yeah, we just want to play around. Feel free to use the script. Everything is on GitHub, as I mentioned, and until next time.